Right, so continuing from where we finished off last time, we showed previously that the independence number of a graph plus the vertex covering number of a graph always adds up to the number of vertices. Okay, now the vertex covering number, remember, that's the smallest number of vertices that I need so that all edges are incident with at least one of the vertices within the particular set. In other words, the smallest number of vertices that I need to cover all the edges of a graph. Now recall the definitions of alpha prime G and beta prime of G. Alpha prime of G being the matching number of G, in other words, the cardinality of the largest matching that I can find, and beta prime G, which is the what is that? That's the edge covering number, right? So it is the smallest number of edges that I need to cover all the vertices of my graph. Now we are going to find, we can actually find a similar type of result for the for alpha prime and beta prime, and basically how we do that is let's take a let's take a maximum matching of a graph G. Let's call this maximum matching M. Right, so there's my matching in blue edges, and then we've got the remaining vertices there. Now using this matching, how do we form a an edge cover? We can form an edge cover by simply selecting all these edges here, okay, and basically then at the very worst we still need to cover the remaining vertices. So basically all these vertices are covered by this set of edges, and now what we do is we need to choose an edge for each one of these vertices at the very worst, right? So basically we can construct an edge cover of cardinality. First of all, cardinality M, right? Okay, plus how many edges are we at the very worst we're going to include how many edges. It's going to be an edge for each one of the remaining vertices, okay? And so how do we count that? We're going to count that as it's going to be the order minus twice the number of vertices covered by the matching, okay? Because it's these vertices here that you're counting, okay? And subtracting that from N, we're counting the remaining number of vertices, and at the very worst we're going to have to include an edge for each one of them. Right, so we can basically pick M, pick a matching M such that the cardinality of M is going to be equal to the matching number. Alright, then we pretty much get that the edge covering number, which is the smallest number of edges that I need to cover all the vertices, is going to be at most this edge cover that I chose, which includes all the vertices of M plus n minus twice alpha prime of g. Okay, and that is pretty much going to imply basically that this quantity here plus that quantity there is, let me just move that a little bit there, is going to be at most n. Okay, so there we've basically constructed an upper bound for the sum between those two quantities. So now the question is, can we construct a lower bound? Perhaps we can also show that beta prime plus alpha prime is equal to n. If we want to do that, we need to find a lower bound. Okay, now we start with a minimum edge cover, an edge cover of smallest cardinality, which is the edge covering number. The blue edges denotes the edges, and those edges cover all the vertices of G. Okay, so just to make it clear there, the black edges are, the blue edges are the edges coming from the edge cover, and the black edges are the remaining edges. Now, if we look at the graph, if we consider the graph, G, that has the vertices of G, and only the blue edges. Okay, so we're going to look at this. We're going to look at this graph here. It's the graph with all the vertices of G and the edge set E prime. Now that graph is going to be the graph without the black edges. Okay, now this graph could be disconnected. If it is disconnected, we consider the components of this graph here. Right, so there's a representation of the graph we talked about. So those are the components. Let's say it's got k components, and there's the representation, only the blue edges. Now the question is, can any one of these components contain a cycle? And let's say it does. Let's say the first component contains a cycle. Well, it means then that you could just delete that edge there, and you would still have an edge cover, because all the vertices will still be incident with blue edges. Okay, so basically what this means is each component of this graph must be a tree. Remember, if a graph is acyclic, then if it's connected, it must be a tree. So each one of these components is a tree. So we can go and count the number of edges that this graph has. Right. So if there are k components, we know what the size of a tree is. That's going to be the size of each component. And so in total, this graph is going to have how many edges? Summing over the total number of blue edges, that's going to be summing over the blue edges of each component. And that is going to be pretty much each mgi that I replace with the order of gi minus 1. So that is going to add up to... Okay, and that is going to be, n of g minus k. Right, now we can form a matching. We can form a matching by just selecting one edge from each component. That is a matching. Okay, so how many such edges are there? There are exactly k such edges. Right, so this means that the matching number of G is definitely at least K, right? But we can write K as N minus K, right? And we said that N minus K is exactly equal to the quantity B prime of G. And that is going to imply that alpha prime of G plus beta prime of G is going to be at least N. Remember we proved that it's at most N. We're proving that it's at least N. Okay, so therefore you have equality. Okay, so therefore this matching number plus the edge covering number is also equal to N. Okay, so if we make a summary, this is Galay's theorem. If a G is a graph order N and with no isolated vertices, then the independence number plus the vertex covering number is equal to N, and the matching number plus the edge covering number is equal to N. Right, so we're going to now prove quite an interesting result for bipartite graphs. We're going to prove that the vertex covering number of a bipartite graph is always exactly equal to the matching number. Now, let's make the following observation. Right, so let's take a matching M, and let's take this matching to be cardinality exactly equal to the matching number of the graph G. Let U be a vertex cover. Such that the cardinality of U is exactly equal to the vertex covering number. Okay, so we're going to color the vertices of U, we're going to color it yellow. Because U is a vertex cover, it means that this is a set of vertices that covers all the edges. So all these blue edges have to be covered, right? So this means that at least one end of each blue edge must be within U. So basically you need at the very least that, possibly that. So for each one of these edges we'll have at least one of its ends within U, right? Okay, so basically what is the implication of this? The implication of this is that the cardinality of U must at the very least be the cardinality of M. And that's going to imply that this matching number of G is at most the vertex covering number of G. Vertex covering number of G. Alright, so we've got that inequality. But it turns out that for bipartite graphs you can actually get equality there, and that's what we're going to prove now. Okay, so we showed that the vertex covering number for any graph is at least the matching number of a graph G. Right, so it turns out that we can prove equality for bipartite graphs. So let's assume that G is a bipartite graph, and we're going to prove that these two quantities are exactly the same. Now, we can prove the one side of the inequality. We know from the previous argument that the vertex covering number is at least the matching number. So all we need to do to complete the proof of the theorem is we just need to show that the reverse inequality holds. So what I'm going to do is I'm going to partition my bipartite graph into the two partite sets U and W, and I'm going to look at M, and I'm going to let M be a maximum matching of cardinality alpha prime of G. Now, what happens if all vertices in U are matched? So there I've got my bipartition, and all the vertices in U are incident with my blue edges, which are the matching edges, right? So we've got this situation here. So we assume that all the vertices are in U are matched. Well, what's going to happen in this case is basically what will this imply? This implies this implies that U is a vertex cover. Now, why is it a vertex cover? Because if I take this whole set here of vertices, like all the edges of the graph are going to be covered, right? Because you can't find an edge there, because otherwise it's not a bipartite graph. Okay, so you can only find edges there. Okay, and when those edges are going to be covered by the vertex set of U. So what is this going to imply? This is going to imply, this will imply that the vertex covering number is at most the matching number. The smallest number of vertices required to cover all the edges, which is beta of G, is going to be at most alpha prime of G. Now remember these blue edges, counting them, I will count this matching number. Right, so this must just be changed to vertex cover, right? Okay, so then the theorem holds. So what we do now is we define the set A. It's a subset of U, and it's just all the vertices that are not matched by this matching that we're talking about. Okay, so we let A be the collection of all unmatched vertices. Now remember from Hall's theorem, we choose the set S within U. It's all the vertices V in the vertex set of G, such that there exists an M alternating path from some U in A to V. Right, so looking back at our bipartite graph, so we define U1 as the set U's intersection with S, and we define W1 as the set W's intersection with S. Right, so let's just quickly look at U. So U1, for any vertex X in U1, you can basically you can find a alternating path, an M alternating path between some U in A, like that, and X. Alright, for some X and W1, you can find an M alternating path between some U in A and X. So you go up, you go down with, and then up again, and then down again, and then up again, and then down, say, for argument's sake. Right, so there you've got the defined sets as I've just described. And now what we do is we make the first claim. We claim that the two sets W1 and U minus U1 as intersection with M is empty. Right, so let's go and look at our sketch again. There are my two my sets U minus U1 and W1, the yellow part colored in. So now what I'm claiming is that you cannot have any blue edges that lie like that for argument's sake. Now what would happen if you had that blue edge that's there? Well, then you would be able to do the following. You'd be able to find such an alternating path from a U in A that goes like that. Red, then blue up, then red down, blue up, red down. And then you could go again blue up to that vertex there. But that's going to imply that encircled vertex must lie in there. But we already assumed that it lies in U minus U1. Okay, so it's clear that little part is empty. Then we also claim that the edges between these two sets, the set U1 and W minus W1, that is empty. So going back to our sketch, there we've got the colored part, which is U1, and then also W minus W1 and U1. Alright, so now what we're claiming is that you cannot find edges, any edges, can't find edges between those two sets. Well, first of all, you cannot find blue edges between those two sets, right? Otherwise, you're going to contradict your matching property. Okay, you can't have that situation there, right? You can also not have a blue edge like that, because remember the way we defined A. Right. So so what happens if there's, say, a black edge? Let's see what happens there. Well, then you can again there will exist a U in A, such that you can find this alternating path, up with a blue, down, up with a blue, down. And then we go up with a blue, and then we go down to that vertex there. So there exists an alternating path between some U in A and Y, and that is going to imply that Y lies in there, which is a contradiction. Okay, so now we define the set B. The set B is the set of vertices U in U minus U1 and W1. Okay, now this set, that's a set that's colored in yellow. Now we claim that this set is in fact it's a vertex cover. Right, so let's just check that all the edges are covered. Now, we need to show that all the edges are covered for this to be a vertex cover. Okay, now remember we said that there are no edges between those two sets, so we can't find edges there. Right, so so basically, right, so the edges could lie there, okay, or they could lie there, in which case they're already covered. Again, they don't lie there, obviously, so again, that is the only thing that can happen there, so that edge will be covered. And again, any edge there will immediately be covered. So that is clearly a vertex cover. Okay, now that we proved that that is a vertex cover, if we can then prove that the cardinality of B, which is a vertex cover, is at most M, the cardinality of M, then we basically have that because B is a vertex cover, this is true. This is at most the cardinality of M, and that will be at most, that will be at most the cardinality of alpha prime of G. Right, so we just need to quickly see why that is the case. Right, so going back there, first of all, note that we said every vertex in U minus U1 will be matched, okay, because we already excluded the unmatched vertices, which we put them in that set there. Okay, so every vertex in U minus U1 will be matched. So all we have to basically do is to show that every vertex in W1 is matched. Right, so let's say there's a vertex Y in W1 that's not matched. Okay, so therefore you can find an alternating path from some U in A that goes like that. It goes down, then with blue up, then it goes down, then it goes up with blue, then it goes down, then it goes up with blue, and then it comes down like that. And that is an M alternating path. It's an augmented path. And that's going to contradict the maximality of my matching. Remember, if it's got an M augmenting path, it means we can construct a larger matching. Okay, so basically the implication of that is that every vertex in W1 is going to be matched. Okay. Now it's important to know that this matching edge can't lie there, because we already proved that we already proved in the very beginning. If you go back, we proved this here, that the matching edges, you can't have any matching edges that go from W1 to U minus U1. Right, so the blue edge we talked about there, it can't go there. It has to therefore go there somewhere. Okay, now what you can do now is, if you go and count, you can now see that if you go and count the number of vertices in B, you see each vertex in B corresponds to at least, to one blue edge. Okay, and this is going to imply, that the cardinality of B, which is now the number of vertices in the yellow set, that's going to be always less than or equal to the number of blue edges, because you could get more than a cardinality of B blue edges. Alright, so therefore you have this inequality chain here. That B is a vertex cover, and so it must be bigger than or equal to the vertex covering number, because the vertex covering number is the smallest number you can find, and the vertex cover that B we showed is at most M, and M is a matching of coordinality alpha prime of G. Okay, so just an observation. If G is a graph with no isolated vertices, if I take an independent set U of that has cardinality equal to the independence number of G, right? And if I take an edge cover of cardinality beta prime of G. Now, what does an edge cover do? It's a set of edges that covers all the vertices, right? So all the vertices in U are going to be covered, right, at the very least. But you cannot have that because U is an independent set. So basically, you are pretty much going to have a situation where each vertex in U is incident with a edge, with an edge from the edge cover set. At least one, because they're all covered. So this is going to imply that the edge covering number of G is going to be at least the independence number of G. So then also for bipartite graphs we can also go and prove that we have equality between the independence number and the edge covering number. And again, how they prove that is, remember we've got that the sum between these two things is going to be n, and we have that the sum between these two things is going to be n. We prove that for graphs without isolated vertices. Right, so we proved that then alpha of G is then n minus beta of G. We prove that beta of G is equal to alpha prime of G. Okay, so we can do that replacement there. And then from this formula here, we get that that's equal to beta prime of G. Right, so we've got equality there in bipartite graphs as well. And that therefore concludes this section.